Lecture on ML Type Inference. This is video number 10, the final video. Content is lambda ML and PTS ML. This is the type system of ML, and this is a type inference algorithm for ML. We study these, and then we also include appendix of the equivalence of lambda ML and lambda-let. So this appendix contains some advanced materials, so this appendix is for those interested readers. Relationship between lambda-def and lambda-let. Lambda-def is the one we defined in the last video lecture, which is lambda term extended with top-level let definition. However, in ML, expression E1, this E1 in let expression may contain free variables, as in this example, where this x is free, right? Therefore, one would naturally think that the ML type system, this one, the Damas-Milnor type system, is more powerful than lambda-def, naturally, and algorithm W, which is complete with respect to this Damas-Milnor, this one, Damas-Milnor system is stronger than PTS def. So this is a natural observation. However, the extra power of this Damas-Milnor system is in some sense illusion, in the sense that lambda-def can directly simulate this Damas-Milnor typing. The simulation is done by eliminating free variables in let definitions. So free variables in let definitions, such as x in this example, here x, this x is free in this expression. And these free variables in this part of let definition can be eliminated by transforming the entire expression to this form by inserting lambda at the time of this definition site to make this closed, and then at the time of usage, here x and x, we apply x to the same free variable x, same as before, this x, right? So this transformation. So this is similarly to lambda-lifting function definitions with free variables. This transformation can be applied in compiler, and so this is non-equivalent transformation, meaning preserving transformation. And as we see later in this lecture, this transformation also preserves typing in some particular sense. So in order to apply this procedure, we note two things. First one is that bound variables must be renamed before the transformation. And also to deal with nested let definitions, the transformations perform from the outside, right? So this transformation increase free variable in the nested let case we will show in the example of this transformation. Lambda-lifting let definitions. This slide defines the transformation in detail. We use notations. Eta is an environment that maps each let variable to a finite set of variables. And this notation is the result of transforming E under the environment eta. This notation is sequentially evaluating E1 and then E2. Standard encoding is this one, right? So this lambda x, lambda y, and return y, so that throw away x. So this is thrown away, and this is returned, so that the entire expression, the notation is same as E2. So this is the actual definition of lambda-lifting transformation of let definitions. Without let definition, right, these lambda expression, nothing happens, so that this is just recursively copying everything. The actual transformation is done by this rule and this rule for the case of let expression, we first inductively transform E1 under this environment and get the result, and then compute the free variables, and then extend this let variable with this set of free variables in the result of this transformation. And under this extended environment, this E2 is transformed to get a result, and then reconstruct this let expression by inserting this extra lambda abstraction. And this is extra term to make the result of the typing same as before, because E2 may not contain x at all. In that case, set of free variables are thrown away, so that in order to prevent this situation, we keep at least one occurrence of x, right? And x inside of this body of that expression is transformed in this rule, so that x is x extended with this application of this free variable x. So this is a lambda-lifting transformation, right? As I stated, this extra term in this result of this let expression, body of let expression, is for type preservation and not essential. So if E2 contains at least one occurrence, then this is not needed. Well, you don't have to worry about too much, right? So this is just to make a technically this transformation preserve exact typing. So this is a definition of let lambda-lifting let definitions. So this is an example. So this is a nested let. Let x is this expression, let y is this expression. Both has a free variable x and y, and the result that here the definition site is lambda x is inserted, and this definition site lambda x and lambda y, these two lambda abstraction are inserted, right? This and this, because this y contains x, and x is lifted with x, so that this y is also lifted not only just by y but also x, right? And then deconstruct this let expression, and then entire let expression is reconstructed. This extra term, this one and this one, is actually in this case not needed, but for the systematic definition of algorithm, we keep this. Right? So this is a simple example. So we are now in position to define the type system of ML, this one, lambda ML, and the type inference algorithm, PTS ML, for ML. Right? So this is the ML type system. This is a definition, so that in order for this typing to be derivable, so this is a rule, kind of meta-level rule. The condition is this one. We transform E by lambda lifting and make a term of this lambda def with empty let environment. And if this term has typing gamma turnstile this term colon tau in lambda def, then this ML expression E has a typing gamma turnstile E colon tau. So this is the definition of ML typing. So we write this way if this typing is derivable under this definition. Right? So this is a type system. It's a meta-level type system by the composition of lambda lifting transformation and top-level type system, top-level let definition type system. And similarly, ML type inference algorithm is simply this one, so that PTS ML of E is just to delegate this E first by this lambda lifting transformation and make this term, and then given to this PTS def. The result is ML typing. Right? So this is quite simple, that nothing nothing extra, nothing complication that arise by only technical ingredient is lambda lifting, and then by just composition of lambda lifting and lambda depth, same as this type inference algorithm. So one note and comment. So type of ML expression, those expressions that has typing are restricted to those expressions that contain no free let variable. Of course, expression can contain free variables, of course, but no free let variable. So as a comment, a free let variable, or the same thing, free variable having a polymorphic type. This is an imaginary entity in ML. That is the one observation. In the second order lambda calculus, free variable with polymorphic type is indeed a legitimate term, but in ML, that is kind of imaginary entity. And that imaginary entity appears in a Damas-Milnor system. That makes various things complicated. That's additional comment. One additional comment about lambda lifting. I just said that lambda lifting, this transformation, preserves typing. This is for comparison with other systems, namely Damas-Milnor systems. In the type system of ML just defined this way, this lambda lifting is part of the definition. So actually there is no issue of type preservation of this transformation. The type preservation becomes important when we compare this type system with Damas-Milnor type system, which will be discussed in detail in the appendix. Let me show some examples in lambda ML. Expressions with a let definition. These are the same as in the lambda, simply typed lambda calculus. For x, of course, obviously this is a typing. Lambda x dot x, this is a typing, and xy, we saw this example at the beginning of this lecture. This is a typing, and this typing is also the same as in lambda ML. Right? So for pure lambda terms, they have the same typings as in this implicitly typed lambda calculus. And also this lambda ML expression with let definition can be also typed. For example, this one, so closed identity function applied to x and y. X and y is inferred t1 and t2, obviously. We have this typing, and indeed, this you compute this typing, then you get this typing. For those with free variable x, so in this term, in this example, x and y are free variables, so that these types must be in the environment, right? And then this has type t2, this t2, right? So this is a nested let expression we gave as an example in the previous slide. Also, so free variable x and y, these x and y are free, and so x and y are in the environment, and this is a result types. Right? So these are just examples, and the important point is that this this lambda ML preserves typing of lambda terms and extend its let definitions. Soundness and completeness of PTS ML. So PTS ML we just defined, right? So we are obliged to show its correctness, namely this is a type inference algorithm, so correctness is soundness and completeness. In this case, however, these are trivial. By the construction of this type system and the property of PTS depth, we immediately obtain the following two corollaries. First one is soundness, and the other one is completeness. Furthermore, this soundness statement is exactly the same as before. So if this new algorithm PTS ML succeed with typing, then any instance, definition of instance is the same. Any instance is derivable. Conversely, if there is some typing under this type system, lambda-ML, then PTS ML succeed with some typing, and there is some substitution is such that this equation hold, right? So that meaning that this given derivation is an instance of this PTS ML typing, right? So these are just a simple corollary, nothing to be done, nothing to be proved by construction of this type system and the construction of this type inference algorithm. So we have completed the definition of ML type system and ML type inference algorithm. Here is a summary of so far we have achieved. So polymorphic typing of ML, so this type system, its essence is this lambda-def. This is just the type system of simply typed lambda calculus extended with top-level let definitions. And there is no, as we have studied, there is no complication. This is just the same as the introduction of polymorphic primitives, right? Map and reduce and so on. And then let definitions with free variables are transformed to top-level definitions, global definitions without free variables by eliminating lambda-lifting. And nice thing about this approach is that it has the same expressive power of the Damas-Milner system and also the same simple properties of this implicitly typed to simply typed lambda calculus. The type inference, ML type inference, is similarly stated. This is composition of lambda-lifting and PTS def. Soundness and completeness are simple corollaries of those of PTS def. So therefore, we have a principal typing. This algorithm computes a principal typing of any given type correct ML expression. So in Damas-Milner system, we understand that there is no notion of principal typing in the Damas-Milner system, but that does not imply that the language ML does not have this property. Indeed, we have achieved that ML, the type system and type inference algorithm, where the notion of principal typing exists, and there is an algorithm that computes a principal typing of any given type correct expression. So in summary, this approach is as simple as this simply typed lambda calculus and as powerful as the Damas-Milner system. So this is a summary of the ML type inference so far we have studied. We have so far completed the contents of ML type inference, the contents we aim at in this video lecture series. And I personally believe that the type system of ML we presented represents the essence of ML. I also claim that this way of explaining ML, this framework, starting with a simple type discipline of lambda expression and the notion of principal typing, is the only account that makes ML type inference, including its completeness proof, accessible to anyone, because this claim is based on the current situation. The completeness proof of ML type inference, I don't think you can find in standard textbook. Or even it's difficult to find a complete proof, detailed proof in technical technical literature and journals for expert. Right? So therefore this claim and this observation. However, the lambda-let, which is the Damas-Milner system, is the well-established standard, and people always talk about that standard type system for ML, and based on that, various explanations have been made. So therefore this appendix. So in order to understand ML, I don't think that this appendix is necessary. However, for those of you or any expert who are in some doubt about that this simple account we have just seen is indeed sufficient or some adequate. In order to answer these questions, I prepared this appendix. So appendix is the technical relationship to the Damas-Milnor system. So this is mainly for better understanding of this Damas-Milnor system. And also some warning. This appendix contains advanced materials for interested readers. This is not for easy to understand. Because of the complexity of this Damas-Milnor system, and therefore some proofs related to the Damas-Milnor system are inevitably complicated and omitted. Right? So here's the appendix. Here's contents of appendix. I restate its purpose. That is, confirm that lambda ML is equivalent to lambda-let, and also further deeper understanding of lambda ML and lambda-let through the non-standard let rule, this rule. So this rule is non-standard, and actually it is quite tricky. I will elaborate this later. So outline of the development. First, I define a type system lambda-let CLS equivalent to lambda-let. This is standard, well-known and often used, and so proof is omitted, although this proof, the detailed proof, is again rather complicated. Second, use this lambda-let CLS to show that lambda-lifting of let definitions preserves typing. The third, define lambda subst, that is, the type system of lambda term with this extended with let construct of this rule, and show its equivalence to lambda-let. This must be verified because this step is an important step to obtain this equivalence. But again, this proof is rather involved. So proof can be found in this PhD dissertation of myself. I believe this can be obtained on the internet. If you can search on this internet, then you can find a PDF document from University of Pennsylvania, I believe. And now the final step is to show that lambda subst is equivalent to lambda-def. Combining everything, we effectively achieve the equivalence of lambda ML and lambda-let. This is the agenda we will be taking in this appendix. So lambda-let CLS equivalent to lambda-let. This is more often used as a type system of ML. This system is given by this set of rules. In the original Damas-Milnor system, lambda-let, we have rules for type abstraction and rules for type application, type instantiation separately. In this system, these two rules are combined into let rule, in this rule. And so that for let expression to have some type tau, E1, this E1, must have some type tau 1, and then E2 must have some type tau, the same tau, this tau, under the type environment, extended with X of this type, this polytype. This polytype is tau with type abstraction for all T, set of T is abstracted. And these set of type variables are those in tau and are not in gamma. Right? So equivalence proof is rather involved and omitted, but this is quite standard. So we omit the equivalence proof. So this is a quite standard type inference used instead of the original Damas-Milnor system. The first technical piece we need to establish equivalence of lambda ML and lambda ret is this property. Lambda lifting of ret definitions preserve typing. So let's go into this first, right? So let is duplicated. This is a term let, and this is English let. Let this expression, let x equal E1 in E2. This is expression, so you can distinguish between the font. This is a typewriter font, and this is font in this slide. So this expression, suppose this expression is given, and let this free value, set of free variable in E1 to be this set. And we use the notation that lambda x bar is a sequence of lambda abstraction, and x followed by x bar is a sequence nested application of this application. And this notation is again the function type, nested function type. And again, this is extension of x1 through xn. Under this notation, we show that this expression is typable in let CLS if and only if this lambda lifted, it's not lambda lifted, this is just one transformation of lambda lifting. So E2 does not transform, but this is enough. So one step transformation used in the lambda lifting. This is the result of one step transformation. It's the same typing under this type system, right? So by lifting everything over the free variable at this point, and then at the use point, application is inserted. This is here to make this complete precise equivalence, because E2 does not contain x at all. But so then this free variable are lost in this gamma, so that to prevent this situation, we keep this at least one occurrence of x. So this if and only if statement, this is now we prove. The first part is if part. So this proof is, so this is a complete detailed proof, nothing involved, nothing complicated, just mechanical analysis of derivation trees, and then you can easily understand. So we do not go into the detail, but as I stated, this is just mechanically checking the derivation tree, and then so then the preservation is proved. The if part is that this original expression is derivable, then this result of lifting is also derivable under the same gamma and under the same tau. In this part, this extra term is not necessary. This is necessary for the only if part in the next slide. The type preservation only if part proof. We suppose the result typing, result of term, and then this resulting term of the lifting transformation, one-step lifting transformation, has some typing, and then the original one is also typing under same gamma and tau. So again, I skip the detail, as the situation is the same as the if part, right? So nothing complicated, nothing elaborate going on, just carefully analyze derivation trees, and then we can show that detail is not so interesting, so I omit the detail. You can stop here and check each detail. Here you have this rule to get this assumption that, right, this gamma is written in this way containing x because of this existence, even if E2 does not contain X. Right. So in order to establish the desired equivalence of lambda ML and lambda det, we use this new type system, which is non-standard, a non-standard ML type system called lambda subst in the intermediate mediator. So let's look at this set of rules. The first rule is just for simply typed lambda calculus, and then we have one rule, subst. So in order for this let expression to be typable, E1 must be typable, and also E2, where x are replaced with E1, this expanded term is typable. You may find some mention of this rule in some textbook, I'm not sure, by referring that this is just a simple macro expansion of, and therefore it's kind of obvious. Now, this rule is potentially quite dangerous, and usually this form of rule does not make any sensible derivation tree logical system. So note and warning. First of all, note, for closed let expression we use this closed subst because so for if the language expression are restricted to be closed, this is closed, then this subst is restricted to be with empty environment. This is just a natural restriction. This is one note. The comment, this is warning, comment is the following. This rule, subst, or same as this rule, this derivation system is not a standard inductive definition because this term, this expression is arbitrarily or unboundedly, well, you can find some bound, but intuitively, on the face of it, this expression is larger, strictly larger, potentially strictly larger than the conclusion expression, and therefore this rule is not an inductive definition, and therefore you can't get immediately the inductive closure of derivation trees we have learned at the second lecture of this lecture series. So, but in this particular case, however, this system, this lambda system, yields a well-founded derivation system. But in order to say this, you need some careful preparation, right? So the preparation is in the next slide. So lambda subst is well-founded. Without this, the following argument, meaningless, right? So it's well-founded so that it's a sensible derivation system. In order for this to be established, we first define that degree. This definition is taken from the PhD dissertation of myself. As I mentioned, this can be found online from University of Pennsylvania. Right? So I believe that this is the first appearance in the literature that this is well-founded, although it will not be mentioned or without, well, this subst may be mentioned in various textbooks, but this technically important piece may not be mentioned. I don't see any citation in this respect in this technical important point, but this is just a side comment. You can find the exact definition in this 1989 dissertation. Right? So let degree LD of L comma E. This is a let degree E under let degree environment L. So this is defined this way. In order for this, so the point is to define the complexity measure of this let expression, so that this measure is bigger than substituting x in E with E1, the potentially bigger expression. So you need to make the measure of this expression bigger than the expanded one, right? So this is an important lemma. So in order for this to be defined, we need some kind of interpretation using environment, so that so x measure of x is 0 if x is not in this domain, otherwise L of x. Now this and this is just addition, and also this is same as E, right? So this somehow count potential occurrences of this x, because potential occurrences of x can be non-trivial because of the nested let expression, right? This is the point of this let degree. So let degree of this let expression is this way, so that 1 means this expression 1 plus let degree of E2, and in this case we interpret E2 with the extended environment, extend L with x to be let degree of E1, right? E1. So this is the point, right? So this is a technical device to make everything consistent. So make sure that this non-standard proof rule is meaningful, right? Well-founded. So technical lemma is this one. Let degree of this is equal to let degree of this expansion, right? So this has one extra one here, so that this is bigger than this term. So we define the complexity measure of expression, ML expression, as a lexicographical pair of let degree of E and size of E, right? Then each rule of lambda subst, the measure of expressions of upper secants, is strictly smaller than that of the lower secant. Therefore, lambda subst is a well-founded derivation system. So we are now safe to use this lambda subst. Under this preparation, we can show the equivalence of lambda subst and lambda let, Darmas-Milnor system and lambda subst. Two theorems, right? So both way of implication. First theorem. Let E be an expression that does not contain free let variables. This restriction is superficially needed, and as I stated as a comment, free let variables are imaginary entity in ML. You don't need, no use of free let variables. So this restriction is superficial. Actually not an actual restriction. Then under this restriction, if this typing is derivable in this system, then the same typing is derivable in the Darmas-Milnor system. This is one theorem. The other way around, again the same restriction. Let variable free expression E, and then if this typing is derivable in this Darmas-Milnor system, then this same typing is derivable in this subst system. Proof is again involved due to the complexity of this lambda let. The detailed proof are therefore involved and omitted. The proof can be found in my PhD dissertation I cited in the previous slide. So next technical piece is the equivalence of lambda subst and lambda def. So we use this as an intermediate system to connect lambda def and lambda let, right? So this is the next step of equivalence, this system and this system. So equivalence, so we need two theorems. That first, this direction. If this is derivable, then the same is derivable in this system. So this theorem, the first part of this theorem. Now we suppose E be an expression that does not contain free let variables. This restriction is nominal in the sense that there is no real restriction. As I commented, free let variables are imaginary one in ML, non-existent, not necessary. So this restriction doesn't make any real restriction. So we assume this restriction, and then theorem says that if some typing is derivable under this lambda subst, then the same typing, same expression under empty let environment, let definition environment, declaration environment, this term with same gamma and tau is derivable in this type system def. Now, this theorem is not so complicated. Just we can just directly show this theorem. So the detailed proof is the following. So to show this, suppose we have this derivation, given any given derivation we suppose, then proof is by induction on the complexity measure we defined of E, right? So complexity measure, because we can't do induction on structure B, right? Because of this subst. So induction on the structure B doesn't work. But still we distinguish cases in terms of the structure B. And then we exhaust all cases. And induction is by this complexity measure. So in order for this to be provable, we define this inductive measure, so in complexity measure, so that we can reason about this type system. So the only non-trivial case is for the let variable and let expression. All the other cases follow directly from typing rules or the induction hypothesis. So now the case for let variable. This is vacuous since E does not contain free let variable. So E can't be X, and therefore the statement holds vacuously. Case of this let expression. So by the definition of lambda subst, we have derivation of this E1 and derivation of this term of the same tau. This E1 is some type. We name it tau of E1. So by the induction hypothesis applied to E1 and this term, we have a derivation of def and derivation of def. Now let so because of this lambda def, we showed that this has a principal typing property. So we can assume that there is a principal typing of E, tau of P, we name it, by the let subject construction lemma on the next slide. So from this derivation, we can derive this derivation by assuming X to have this polytype of this principal type with the same type tau. Then by the rule let, we have this derivation and we have done. So only missing piece is this let subject construction lemma. We will show this on the next slide. So let subject construction lemma of lambda def, this name I gave to this lemma. So if you have some familiarity with type theory, then you are familiar with subject reduction property. The converse is sometimes called subject construction, and this is that property for let reduction. So the name. So the statement is this one. Suppose you have a typing of this expanded term, replacing X with E1, and that expanded term has typing, and also a principal type of E1, right? Then this principal typing is extend this delta with X to have principal type, principal polytype, E2. Then E2 has same type tau. So this is the lemma we used in the previous proof of equivalence. Right? This lemma is actually not so complicated, intuitively clear. That is the principal typing, power of principal typing. Principal typing can be instantiated to any typing, right? Any occurrence of E1. That is the intuitive idea. Just you only to write down that property, right? So by induction on the structure of E2. So this is just a simple structural induction of this E2. And only non-trivial case is this one. E2 is X, then X gets replaced with E1, right? So given derivation is this one because, right? So E2 is X, so X becomes E1, so derivation is this one. Now suppose this is a principal typing, then there is some S such that this equation holds. By the rule let bar, so this equation holds. This derivation is obtained, right? Right. So you can take any substitution that match this one. So that's the only thing we need to do. All the other cases directly follow from the typing rules or the induction hypothesis. Right? So this is one lemma, and so with this lemma, the previous direction of equivalence proof is completed. One remaining other direction. Now finally, the other direction of equivalence proof theorem is this statement. Again, we assume that given E is let variable free, and then statement is the following. If this term under empty E, empty let environment, empty let definition, this typing is derivable in lambda def, then the same gamma and tau is derivable in lambda subst. So proof is the following. We suppose arbitrarily derived typing of this term, then proof is by induction on the complexity measure of E. Again, we distinguish cases in terms of the structure of E. So cases other than X and this let expression are trivially follow from the typing rules or the induction hypothesis. So the case of X let variable, since E does not contain free let variable, this is vacuously true. So for the case of let expression, by the definition of let def, since this is derivable, this typing is derivable, there is some typing of E1 of some type. I named this tau of E1, and this typing of the same type tau under this X colon this polytype of this tau of E1, right? These are from the definition of lambda def. So by the induction hypothesis applied to E1, this one, we get this typing in lambda subst. So we can't apply induction hypothesis to this statement because statement is this form. However, by the let subject reduction lemma on the next page, from this derivation in def, we obtain this derivation, this term, E2, with replacing X with E1. So the term obtained from E2 by replacing occurrences X with E1, this expanded term of the same gamma and same tau. From this derivation, we obtain this derivation by lemma. We will show in the next page, in the next slide. Then by the induction hypothesis, now we can apply induction hypothesis to this term because we are doing induction on the complexity measure of E. So by induction hypothesis applied to this derivation, we obtain derivation in subst. So the conclusion, the desired conclusion follows from the rule let, right? So the only missing piece is this let subject reduction lemma. The final piece is this lemma, let subject reduction lemma of lambda def. Lemma stated the following: if this term and this term is derivable, then this term is also derivable. Now you can see that from this and this we have a let construct. This is a two premise to conclude let construct, and this is a result of let reduction. So this can be regarded as the preservation of typing through let reduction, so the name of let subject reduction lemma. Proof is by induction of the structure of E. Again, the only actual case is this X. Other cases follow immediately from the typing rules or the induction hypothesis. Right? So for this case of let variable, the given typing become X. Here E2 is X, so given typing is this one. So by the rule let bar, there is some substitution S such that tau equal S of tau 1, right? So this is by the rule. And then, since this derivation is an instance of this derivation, we didn't formally define instance inside of this typing derivation, but this is an instance by applying substitution and adding some extra assumption. So we have this instance is also derivable because this is derivable. This is a simple mechanical type substitution lemma usually hold in any type system, and here we omitted its details. So now from this lemma we completed the other direction of equivalence and completed everything. Relationship between lambda-ML and lambda-let. So we have established the following. First, lambda-def and lambda-subst, which is a version with closed let restriction, are equivalent. We have shown this in detail, right? And since lambda-let and lambda-subst are equivalent, combining these two, we obtain lambda-def and lambda-let are equivalent under the restriction that let expressions are closed, represented by this rule, where this E1 is restricted to be under the empty type environment. Then, combining everything, we have finally this one, lambda-ML and lambda-let are equivalent. Right? So this is the desired conclusion we have shown using known result of equivalence. So now here is a final remark on type inference. So we observe that PTS ML and algorithm W are equivalent. This is under the assumption that W is complete with respect to this lambda-let, lambda-Smirnov system. And this is kind of well-known fact. So one observation about algorithm W is that algorithm W can be regarded as an ad hoc optimization of this simple framework. Ad hoc doesn't mean anything bad. Ad hoc is an well-engineered optimization, well-engineered on some particular aspect of ML. So this is one way of understanding W. Some elaborate definition of algorithm W with respect to this a little bit complicated type system, right? So now that this is a final concluding result of this appendix. Now we review the entire type inference lecture, we have learned the following. First, we started with inductive closure as the basis of language definitions, so that we can apply the notion of induction on derivation trees. We do all the time. And then we carefully analyze the implicitly typed lambda calculus. And then we introduced principal typing and type inference strategy and defined PTS and showed in detail that that algorithm compute a principal typing of any lambda expression. And then we defined the extension with closed-let definition and show that this is enough to type ML, so type inference system of ML. And now in this appendix, we show that this resulting system is equivalent to Darmas-Milner system. So I hope that you enjoyed these contents through this video lecture. Possible further topics of this channel include implementation method for ML type inference, type theory and operation semantics, and typing various advanced constructs such as record polymorphism of SML#, and so on. So comment and question are welcome, and you can put a comment as a video comment in YouTube and so on. So this is the end of this entire type inference video lecture.